I'm hoping that this little talk, which I'll try to keep relatively brief, is mostly revision. It's mostly looking at things that you have already looked at in junior secondary physics or junior secondary science, the physics dimensions thereof. But hopefully looking at it maybe a little bit more carefully with a little bit more of a senior physics attitude, and just reminding ourselves, because this is kind of laying the groundwork for other things that we need to talk about as we go. So I have this motorbike. It's pretty old. It's a 1999 model. It's pretty dodgy. I spent $4,700 on it. So, but being a motorbike and being a 1200, it will do 0 to 100 kilometers an hour in about 3.5 seconds. I don't quite get to that because I'm not a drag racer, but you know, it gets up there pretty quick. If I sneak past you at the lights and sit at the front, you're not going to be waiting. Let's put it that way. So we probably should, because we're doing physics, use SI units. So instead of 100 kilometers an hour, we'll call it 100 divided by 3.6, and there's reasons why that is, and we can explain that if that's not clear. It's basically got to do with the fact that there are 3,600 seconds in an hour and 1,000 meters in a kilometer. So when we're dividing them, we end up with 100 divided by 3.6, which is 30-ish, maybe a little bit under 30, 28, something like that. So from 0 to 28, let's call it, meters per second in 3.5 seconds. So what we're talking about in motion is looking at what's happening with those motions, what's going on with those. But let's start with a simpler motion first. Hopefully at least one person is old enough to get the joke. It's a long way to the shop if you want a sausage roll. If I want to go from my home here to the shop to get a sausage roll, I can't go directly because there's a big pond in the way. So what I'm going to do is go north up my street for 800 meters, then go 1,400 meters east across that street, and then 800 meters south again down another street to the shop. So the total distance that I've traveled is 3 kilometers, 3,000 meters, if you just add those up. But my displacement, how far I am from home where I started, is only 1,400 meters, if as the crow flies, in a direct line from home to the shop. But I have to say a direction. I have to say I'm 1,400 meters east of home, because otherwise, if I just say I'm 1,400 meters from home, that's a circle of radius 1,400 meters from home where I could be anywhere on that circle. So I have to specify a direction. So distance, we don't care about the direction. We did 3 different directions and just added them up, it's all fine. Displacement, we do care about the direction. So I'm 1,400 meters east of home. Speed is similarly to distance, we don't care about the direction. So it's how fast we're covering distance, how many meters per second, and that's where the unit arrives from. How many meters am I covering every second? So speed, but we don't care, we can just give it as a number. I'm doing 60. So if you get a speeding fine, they don't say you were doing 120 northwest. They just say you're doing 120. So speed, we don't really care about the direction. Velocity, we do care about the direction. So it's the rate of change of our displacement. So how far we are from some origin point or from some defined point. How fast is that changing? How fast are we changing the number of meters that we are away from that point? We go back to this diagram. My velocity would have been quite weird because I would have been going directly away from home and then at an angle and then sort of kind of toward home. So the actual, if you drew a little line from home to me along my journey, oh, it's quite tricky doing this, then the direction is important as well for velocity. So we could figure that out. We can use this equation, velocity, this V represents either speed or velocity depending on whether we pay attention to the direction or not. The S stands for distance, interestingly, and the T for time. So velocity equals change in distance, the little delta means change in, over change in time. How is my distance changing as my time changes? Or for velocity, how is my displacement changing as my time changes? So the two things are related but not the same, and we have to be specific. And when you're writing a velocity, you have to have the number, how big it is, the magnitude. You have to have the units, meters per second, and you have to have a direction if you're writing out a velocity as an answer. Acceleration is the same thing, and actually just mentioning in passing, those who do have some calculus, you know that we have a tool for finding out the slope of a curve. And remember that a rate is just the slope of a curve. If I do a distance versus time graph, then as my distance is increasing as my time goes, that curve has a slope, and that's the rate, right? And so that's going to be the speed or the velocity. And we have a tool for that. It's called differentiation. So if I find the derivative of that line, the equation of that line, I know what the acceleration is. Oh, sorry, the velocity is. If I have a velocity versus time graph and do the same thing, I can find that slope, that rate, and that's going to be the acceleration. So that's where the calculus comes in. You don't need it. So if you're freaking out right now and going, I don't know, I'm not comfortable with the calculus, don't worry. But for those who do know it, it's kind of cool. And we can talk about also what's represented by the area under those curves. And we have a tool for that as well. It's called integration. And we can find out things from that. So I might just do a little kind of side piece for those who are interested on how the calculus fits in. All right, so acceleration is the rate of change of velocity over time, and the rate of change of velocity can mean either getting faster and slower in one line or changing direction, because remember, in velocity we care about direction. So if we go around a corner at the same speed, we're doing 100 kilometers an hour, we go around a corner, we are still accelerating because we've changed our direction of our motion. So the equation is similar. Acceleration is change in velocity, delta V, over change in time, delta T. You can accelerate in the same direction as your velocity or in the opposite direction. So let's just consider one dimension for the moment, left and right, forward and back. So if I'm on the motorbike and I'm accelerating, getting faster and faster, then my acceleration and my velocity are in the same direction, the forward direction. If I see a dog come out onto the road and hit the brakes hard and start slowing down, then I'm still traveling in the forward direction, my velocity is forward, but my acceleration is backward. I'm slowing down in the forward direction, which is equivalent to speeding up in the backward direction. So my acceleration is the opposite of my velocity. We call that a deceleration sometimes, but it's just an acceleration. Same units, meters per second squared. It's just about the direction of the two things. This is a concept that students often struggle with because they assume that acceleration and velocity are always in the same direction. So hopefully it's helpful to understand that they can be in the opposite direction. I said left and right, forward and back, and I used the directions north, south, east and west in my earlier diagram. The motion is relative to a point. So in that case of the home to the shop, motion was relative to home. That was kind of the origin of that system. In our one-dimensional motion, let's call left to right positive because in English we read from left to right. In Japanese they read from right to left, so they might choose it the other way around. It doesn't matter because it's relative. This is one of the things Galileo taught us, was that motion is relative to a frame of reference and we get to choose our frame of reference. We get to decide which we consider to be positive motion and negative. If something's falling, do we decide that down is positive or up is positive? We can decide, but we just have to be consistent once we've made a decision. We can't mess it up in the middle of a question. So the motion is relative. The acceleration is, as I say, possibly in the opposite direction to the motion. There are three equations of motion. You probably don't need to memorize them because they are, you'll be using them enough. If you do the problems, do the questions, do some thinking with them, then they'll actually percolate down into your brain and you won't need to do flashcards or get your partner to quiz you on them or whatever to memorize the equations. They'll just be part of you. So if we define u as the initial velocity, v is the final velocity, if I'm doing my 0 to 100 kilometers, I'm doing 0 to 28-ish meters per second. So u, the initial velocity is 0, v, the final velocity is 28-ish. So the change in velocity, the delta v in that acceleration term, is just going to be the final minus the initial. It's going to be 28 minus 0 is 28, divided by the time. The time is going to be 3.5 seconds if I'm going as fast as I can possibly go. And that means that my acceleration is 28 divided by 3.5. So I can't do that in my head, but it's about 8-ish, somewhere in that vicinity. So that means I'm doing about 8 meters per second squared as an acceleration. And that might ring a little bit of a bell because we know that the acceleration due to gravity when something's falling is 9.8 meters per second, almost 10 meters per second. So I'm doing about 0.8 g. I'm not pulling 1 g of acceleration, but it's pretty hard. I'd better hang on to the bike because I'm accelerating quite hard when I'm doing that. We can rearrange that equation, a equals v minus u over t. I did set these equations up much nicer so that the fractions were proper fractions, but switching from one computer to another seems to have broken that, so I apologise for that. But v equals u plus at. So if you remember that velocity is the initial velocity plus the acceleration times the time. And that kind of makes sense. Like how fast you're going now is how fast you were going initially plus your acceleration and how long you've been accelerating. Right? It kind of seems logical. The units make sense. Velocity is in meters per second. Initial velocity is also in meters per second. Acceleration is in meters per second squared and time is in seconds. And that cancels out to make meters per second as well. So all the units all the way across are meters per second. Again, don't freak because you're not seeing it in front of you, so it might be a bit hard to imagine in your head. We will be doing some problems and some discussions to make sure that it's all really clear about what's going on with the units. The other two equations that we also need, and we won't do the derivations of them now, but we'll just have them. So distance equals ut, initial velocity times time, plus a half at squared, and that should be a squared. That's another equation that's broken. So distance equals ut times a half at squared. And again, if you work through the units, you'll find out that it makes sense. And v squared equals u squared plus 2as. If I were you, I'd be writing these down now and writing them down correctly. V squared equals u squared plus 2as. Square of the final velocity is the square of the initial velocity plus twice the acceleration times the distance covered. Right? We have these three equations. We'll do some examples and some practice. I'll give you some practice questions to do with those. And that is really all that I wanted to say. And I wish I hadn't gone to that screen. But that's a really quick précis, hopefully, of velocity, acceleration, displacement, distance, the fundamentals of motion that we need to discuss Newton's laws and a whole bunch of other things.